keep the number of slides short enough that we can have a bit of a chat afterwards. And I want to keep the presentation informal enough that everybody feels comfortable to have a discussion, because I'd actually rather if we just had a big room and we could all just sit around and talk about the topic than me have to be a talking head for 45 minutes. But that's not the format. The format is I'm giving a presentation. But just to loosen everybody up, could someone please interrupt me? Anybody? No. Okay, brilliant. All right. And could I just get a show of hands? Not for anything, but just a show of hands? Brilliant. Okay, thank you. We're all here. All right, so what we're here to talk about is statistics. So there's a reason this slide exists. There's a reason that people say lies, damn lies, and statistics. It's because it's very easy to fail to understand some small aspect of how a statistic is derived and then get radically the wrong conclusion and take a potentially dramatic decision on the basis of a piece of evidence that's very well trusted. So verification is about avoiding this problem. Verification is about evidence. It's about the role evidence plays in our lives. It's about the challenge of gathering data that we can trust so that when we draw a conclusion, we don't get caught out by our first principles not being thoroughly checked. And it's about communicating that evidence to other people in ways that they can understand. So I'm going to try and do that today, communicate some pieces of evidence to you in ways that I hope that you can understand, and together arrive at maybe a bit of an understanding of how to do that. Now, I'm not a statistician. I'm just a computer scientist, right? Now, my guess is that a solid thirds to three-quarters of this audience is going to be better at maths than I am, and that is fine, because it takes all kinds. So I'm a software engineer, and I've done a lot of ongoing learning to get to grips with this particular topic. So what's this talk structure going to be? So I had a lot of feedback that this section there, examples and maths, really should be cut down as much as possible. And everyone wanted to talk about kind of the number 4 and 5 stuff as much as possible. Now, I sort of drew a line. I'm like, look, I understand that everyone here is in software, which is understanding how to write software, but there's just a certain amount of understanding the problem that you're trying to solve that you need to have in order to come together to work on this kind of problem. So we're just going to go through some basic techniques and then talk about things that you could just like go away and usefully do. And even if you don't know a lot, you'll get some bang for your buck by doing these things in your own time. If some of them seem simple, I'm not trying to insult anybody's intelligence. I want to make sure that this talk is very accessible. So what's the background? The basic terminology is verification is the comparison of something with the truth, for some definition of the truth. Frequently, it's very hard to really pin down what the truth is, and as soon as you try to focus on that and unpack it a little bit further, you discover that your truth is not so much the truth that you thought it was. One particular example of that at work is that we measure where lightning strikes occur. We have observations of where lightning strikes occur, but they're actually only accurate to the nearest 6 kilometers. And so if you believe that that's the truth, you also need to understand that it's not the perfect truth. And so a lot of statistics and verification is about what's a valid inference from a particular observation or belief about the truth, in as much as it's about a statistical technique. There's a lot of intersection with data science techniques, which is really, if I went to work and said I'm a data scientist, 400 scientists would turn around and go, you're not. This is how I feel about data science in general. It really requires a community of people to bring it together. And I'm a bit awkward about it as a buzzword, but it does just mean exactly what we're about to talk about. So here comes the hard bit. So this is not a very hard bit. This is a comparison of some megacorporation.com versus the official Bureau of Meteorology forecasts over a period. And what this graph is showing you some things about what we believe is the truth of our performance. Now, you could imagine drawing a graph like this to compare your company against another competitor. So one of the first points is just that visual communication isn't a Mickey Mouse tool. It's actually the first tool that everyone at work turns to. It's not the last tool, it's the first tool. Visualizing your results to yourself is the key aspect here. So the first thing that we can see is that blue line at the top, that's megacorporation.com. and they're a little bit out. This scale on the y-axis is root mean squared error. For those who aren't familiar with that, what it is it's a kind of representative amount in the unit that you're talking about. So here we're talking about temperature. The unit is in temperature, and it is basically more or less the amount that you're wrong by representatively on average, calculated a particular way. So the first thing you can see is that the next two lines are both alternative Bureau of Meteorology systems, and they're both very reliably a bit better than megacorporation.com. Now, what's important about it is that there's a predictable difference. You know, if the difference is very regular. It's very precise. Now, down the bottom there, we see this thing here called bias. And what that means is the predictable component of that error. So we've decomposed that difference in the first sort of margin up there into the part that we can understand easily and the part that we can't. And bias just means if you consistently added or subtracted a certain amount, you would just always be more right. So what this means is that megacorporation.com hasn't realized that if they just added about a half a degree, they would just always be better. So it's, you know, these sort of basic techniques, you know, they're not deployed by major companies. You know, these people have the resources to go, oh, hang on, I think I should add, you know, some small amount to my temperature forecast. Now, I kind of agree. It's not especially important to be completely perfect about a temperature forecast, but it is a good way when you come back to understanding a complex system to go, oh, this is a little bit out, or, you know, be more exact. You know, you can use it to push yourself to a greater degree of exactness. Sometimes, you know, you need to understand the impacts of an error in order to decide whether it's important, and perhaps that's why this particular example hasn't been corrected. Here's another graph. So what this here shows is the performance according to something called an S1 skill score, which I'm not going to describe other than to say small is good. It's like golf, you know, your score system like golf. And what we have here is the progression of this skill on mean sea level pressure. Nobody's very directly interested in mean sea level pressure, but it means that we've got the structure of what's going on in the atmosphere generally right. If you were appallingly wrong about mean sea level pressure, you couldn't be right about everything else at the same time. So it's sort of a representative thing we can look at. But once again, the observation network is somewhat sparse. The definition of true is up for debate. Nonetheless, it's pretty undeniable that there's been a general downward trend over the years. So one of the things you can use that to say is our investment paying off. If you understand what the S1 skill score means in terms of impacts for your customer, then you can use it to justify a business decision. If you just understand what it means for your scientific algorithms, you can justify scientific direction, write up a research paper, agree to pursue a particular direction of research, etc., etc. Once again, the use of the visual means of communication of these ideas is especially critical. Very few people will walk around with a working understanding of the performance characteristics of these systems as numbers. Everyone will pursue a visual means of comparison. And one of the things that does is it hooks into all of our spatial sort of awareness around, you know, the weight of things visually basically works pretty well. It's sort of the best way to hook into other people's intuitive ideas about the scale of things. And then you can work as a scientist or a data scientist or whatever to make sure that you've crafted this graph that you can understand. The other thing is you can't really just understand it at a glance. Like I've spent like way more than I want to of this talk just pointing at lines that go downwards and explaining what they mean. And this will happen. You know, people need to increase, I guess, like their literacy around these things in order to understand a graph fast, as opposed to, you know, take some time to digest it. But if it's a written report or something, you know, it's not such a big deal. But for a presentation like this, you know, I got a lot of feedback like there's too many lines. And I haven't talked about what all the lines mean. And does it make like, what do all of those blips mean? Are there any events that I could plot on this that explain aspects of that graph? And why does that one line stop and the next one start? So there's a lot of non-communicated aspects to this graph, but they do all mean something. So for people who are, I guess, if you have a culture of communicating through a particular plot, a particular set of metrics, you can use this approach. If not, not so much. Okay, so what it can do for you, I tried to put some thought into what it can do for people who aren't forecasting things. So has anyone ever here tried to predict anything in their workplace? Heaps. Awesome. Okay. I don't really need to go into that a lot further. For those who haven't tried to predict anything, I can imagine the kinds of things you might like to predict are anything that either has something of personal interest, like machine learning is incredibly interesting and more accessible these days, and that's how I got into it in the first place, which was just because it was fantastically interesting and fun, and not at all because I cared about it from a work perspective, but I've now pulled the two together. So I'd actually say don't try and solve a work problem, just get interested. But if you do have a work-related problem, server load, capacity, failure rates, you could try getting into developer metrics, but that's a minefield anyway. Okay, so interesting things to do. So this next part of the talk, I want to talk about things that you could just go away and just do, like some super easy things that if you've got nothing else you want to take away from the talk, like practice doing these. You know, make a graph, derive some simple statistics, find out what your competitors are doing, and then some of the dangers in there. And then what are the big problems? So this is looking ahead more to the last part of the talk, but the existing tools are a bit clunky and deficient. There's some amazing tools, but they're not really they don't completely cover the kinds of things that we sort of really want to do, and that I think that software engineers and the open source community could bring to enhancing the experience of working with statistics and make them more accessible. And then, yeah, so this last point that I think software engineering and science, even though they've been working very closely for many years, I think it can go further, and I think it can go further in open source. That said, Python is one of the best languages in the best communities already. So the first kind of simple plot is a scatter plot. Hands up who just understands this at a glance. Cool, so like most of the room. Okay, that's great. Now, hands up if you think that this is one of the best ways to start looking at data. Not very many. Okay, now that's interesting to me because this is one of the first ways that I tend to start looking at data. And one of the reasons for that is that most kinds of relationship can be visually detected in a scatter plot. So I personally feel like if you wanted to communicate to someone who doesn't understand a lot about statistics, a scatter plot is something you can show them and you can talk about the inherent visual structure in the diagram. And for someone working with things, if you have a kind of a hypothesis that you want to understand, a scatter plot is one of the best ways for you to just visually, without having to manipulate or process the data, to just throw it up visually and get your first visual understanding of what's going on. So what this is showing is a slight negative correlation between the two variables that we're looking at. A perfect positive would be sloping up at 45 and a perfect negative would be down at 45. So what this is showing is a weak but definite relationship between the two. So for me, I feel like it's one of the, it's quick. It's also pretty true. Like you haven't had to do a lot of data manipulation to arrive at this graph. But anything that's point-based, you've often, if it's not point, if it's area or time-based, you often end up doing a bit of interpolation or a bit of averaging or a bit of massaging. And whereas this gives you a pretty direct look at underlying data, which I find pretty useful. So for me, it's well worth doing. The other one is a spatial plot. So in this particular case, what you can see is weather systems have an inherent spatial structure. It's immediately visible here that there is a spatial structure to what's going on. A system's an object-based way of understanding the data. If you didn't have this, it would instantly be apparent if you compared this to noise or something like that. So particularly at investigative stages of the analysis, when you don't know what the best plot to communicate the true essence of what's going on, I think these are some really good techniques. The next thing that I'm going to move into is probably where I expect, well, it depends on exactly who showed up, but this is where we might lose some people in terms of the number of hands that get thrown up. So hands up if you know what a p-value is. Okay, still lots, but definitely fewer. Okay, so P-values are, you know, the standard double negative thinking. It just confuses everybody. You know, who doesn't not understand this? Okay. So I think one of the big problems with it is this double negative thinking. But in general, at least as I've used it, which is not completely extensively, but just for some basic work, some online work, and a few things of my own, it's the probability that I'm just totally wrong about my assumption. It's you know, it's the most basic exception message that you could have. So if I've done something interesting, then it's very unlikely that what I've done will mean nothing. And so, so basically, a very, very low p-value means that it's almost certain that at least something is happening in what you're doing. And generally, I regard it's very much the starting point, but not the ending point. It does make a few assumptions, or at least depending on the specific implementation of the p-value that you've chosen, it can make a few assumptions. So for anyone who hasn't done one before, there's this one in SciPy called Mann-Whitney-U, which rather than working with the absolute values of the data or the distribution, will work on a comparison of how many elements of the first one are bigger than elements of the second one, and use a sort of ranking approach and then look at that. So it sort of takes away a little bit of some of the assumptions that you might be making, and it's a little bit more robust than some of the other choices. So if you have a hypothesis, like more people wag work on Fridays, you can break up your data into Fridays and the rest of the week, and you can run a p-test, but that doesn't mean you're right about the cause. So for example, there was a great Dilbert cartoon saying, you know, 40% of annual leave is taken on Mondays and Fridays. This is a terrible, terrible thing. Well, it's true, but that's also 40% of days, right? So you do need to realize that it's the starting point. The next thing that will be, I think, familiar to everyone in the room, but potentially, if you're going, well, is this true? Okay, like, let's look at how many days it was more than average or below average and try to calculate something. If you're not careful, your above average days will actually cancel out your below average days, because you'll be above the mean, then below the mean, and it'll average out. But actually, you're wrong by that amount quite often. So if you want to know how precise you can be, rather than just what the average is, stay positive. Square everything. Oh, I love that meme. Okay, so I want to talk now about where you go after you've done it. You've got this idea, you know, you've broken your data up into, you know, Monday and Friday because they're around the weekend versus the rest of your data, and definitely like something is happening, but you know, maybe it's not. Maybe the cause is wrong. Maybe you've got 4 or 5 factors in your data that you want to do, and you now need to test specifically whether your hypothesis is right and how much of what's going on can it explain. So root mean squared error is a good way of doing that. That's where you take the above the mean, the positive error, below the mean, negative error, you know, and work with them as both contributing to problems or error. So that the idea is you want to be precise. You don't. Sometimes you will actually only care about the positive error or only care about the negative error. That does happen, and we do get into it. It's a really good starting point. And the fundamental advantage is when you say to someone, oh, well, we have an error of about 2 degrees, they don't need to understand something complicated about statistics, because everyone in the world understands the degrees. Or if it's not degrees, you can go number of days of leave. Your manager will already understand the concept of days of leave or hours worked or something like that. You don't need to explain a new unit of measurement to them. The one that I particularly like is this one called Rsquared. So if you have some kind of prediction and the sort of points which occur, so the idea is the dots represent points that actually happened, and the line on the right, the F, represents your sort of forecast about what happened, and the Y bar on the left represents the average of what happened. The R² is basically the difference between assuming that the mean was going to happen in terms of this, you know, the amount, so the difference between the observed and the average, versus the difference between the observed and your forecast. And so that relationship is actually really solid in saying, well, if you've managed to reduce the area compared to the mean by a significant amount, then, you know, like you've nailed it. Your forecast has a lot of explanatory power. You can feel quite confident that what you've done is a good thing. So this is a fairly easy to calculate kind of metric. It's something you can do. It's something you can do fast. It's not mathematically complicated, and it's explainable. I've basically just said all of that. Okay, so one of the things about the R-squared is that it does use the mean, the thing over on the left, as the basis for comparison. If you have 3 or 4 alternatives that you want to evaluate, if you're in a forecasting situation, you can either compare their R-squared values, or what you can do is say, in some case, the mean is so rudimentary that it's not actually a good basis. So like at the Weather Bureau, rather than saying we compare to the average temperature all year, day or night, hey, we nailed it. We we compare it to climatology, which is the average long-term expected value of these things. Okay, so what you can do then is establish a reference standard for the basis for comparison. Okay, this is something else you can try at home. I'm not going to explain what you can do with this table of values, but there are an enormous number of metrics that you can calculate based on correct forecasts, false alarms, misses, and correct negatives in terms of establishing different kinds of skill score for your system. And the various ones will penalise different kinds of biases differently. So for some people, if you have a lot of false alarms, you'll have a kind of boy who cried wolf problem, and your system won't be valuable. On the other hand, a lot of people are very sensitive to misses. You know, they might be very sensitive to something occurring that wasn't forecast, and so they want to hear about it even if your confidence is low. So you can use this essentially table of values. You could just start recording this database. That'd be a good first step. And then you can go in and look at some of the metrics that are linked to in terms of further information. In the interest of time, I'm not going to talk about the general form of a skill score from that matrix. Gotchas, hidden variables are a gotcha always. So just make sure that there's no magic bullet to a hidden variable that you don't know is there. You know, that's where you think that one particular cause is leading to the consequence, but you don't understand it's actually related to another thing that you haven't included in your model. There's no magic bullet, but what you do need to do is make sure that you've had enough consideration of what's going on. So that might be, you assume that people are more likely to take sick days on Mondays or Fridays, but actually what's going on is you're more like, no. So I've tried to come up with an example on the fly and failed. I was going to say people are just more likely to take a long weekend, but those two things aren't related. A hidden variable is more likely to be a related concept. But there might be things that you fail to capture in your model which are leading to the same cause from the apparent inputs, but there's more thinking that you need to do. Rounding can lead to problems. We had a problem where our observers were writing down the temperature. This was actually a number of years ago, like we've moved on, but they would have to write it to the nearest half degree or maybe whole degree, and they would round up. So they were told the direction of rounding, and this actually introduced a bias into the observations. So instead of rounding up, we told them to round to the nearest odd number, because that would be up or down roughly 50% of the time, you would assume. Scale variance can be a big deal. We have the weather models do very well at broad scale, but don't necessarily capture topography. So if you assess them at a fine scale, they'll get a very bad score in many situations. But if you assess them at the broad scale, they've got really a lot of skill. And it's not just a matter of being fair to the models, it's you can understand how to, like what is a valid inference? Where is the skill? Is the skill in the broad strokes? Is the skill in the detail? Can we unpack the kind of inferences that we can support from our data analysis? Scores can be sensitive to data size. So sometimes if you just have a prediction system and it's got a pretty kind of constant set of skill, and you run it over a small amount of data versus a large piece of data, sometimes various metrics can penalise the inclusion of the additional data, even though basically the performance hasn't gotten any worse. And a lot of the more sophisticated scores are about including factors that avoid these problems of penalising large data sets. And then errors and observations, which I've talked about already. Okay, I wanted to talk briefly about thunderstorm forecasting to make this more concrete. So this is something that I'm doing at the moment at work in a very prototyping, researchy kind of way. You know, we haven't really got hard evidence yet. I just wanted to introduce the audience to the concept of coming at this maybe from the first time. So thunderstorm forecasting is often more about forecasting the direction and speed of movement of currently existing thunderstorms, because that's relatively easy, as opposed to the development of a new thunderstorm from scratch out in the environment, which are called in situ storms, or as I like to think of them, ninja thunderstorms. And that's the only reason I put that in there, is because I like that slide. So one of the things that the thunderstorm forecasting is often assessed on is the speed and direction, accuracy of the predicted movement of a thunderstorm. But I find that's really abstract. You know, people aren't directly, there's no physical phenomena a thunderstorm. There's physical phenomena, rain, hail, lightning. You know, those are the impacting aspects of a thunderstorm. So while we use the thunderstorm as an abstraction to describe what's, you know, going on in the atmosphere, when we want to link that to impacts on people rather than just understand it more abstractly, we need to go into something like lightning. So this is where we took 3 of our thunderstorm warnings, counted up the number of lightning strikes that were in the area versus out the area. So this doesn't support that full table, because this is assuming a warning is present, what happened, rather than a generalized analysis of what happens when we don't have a warning out. But what we can see here is that we can calculate the probability of a detection. So given that there's a warning out, and given that a lightning strike occurred, what is the probability that it's one that we forecast versus being hit by something unexpected? So in a warning situation, there's still a 40% chance that if you get hit by lightning, it's not under a warning area. So for that specific warning. So I really don't, I would genuinely expect that this wouldn't generalize. That's just like one example. But I think it's enough of a, when it's the first thing you look at, it's enough motivation to go, I should investigate this further. It's probably important that people understand something about our thunderstorm forecasts if they care about lightning. So it's the kind of thing where there's the presence of additional evidence to support us doing a greater analysis of lightning risk. I've done the same thing with very, very heavy rainfall. Oh, wonderful. It projects just fine. So what we can see here is that in some of our warnings, so the first ones, the very heavy rainfall pixels are entirely in the warning area, in the threat area. But later on for these other warnings, there's actually a very high amount of very heavy rainfall occurring outside of the thunderstorm warnings. Now, very heavy rainfall, we need to unpack that further. Is there anything else that causes very heavy rainfall in other warning products? Are people expecting to get multiple warnings about very heavy rainfall, or are they just looking at the thunderstorm warning? So a lot of the time when you find a piece of evidence, all you have is about 1 million more questions. And arriving at what's important to communicate is a lot of the problem. Because I mean, I could come here with just like 1 million pieces of information about thunderstorms, and no one would walk out any of the wiser other than Tennessee probably doesn't understand what's important about thunderstorms. You really need to, this is more the tools you use at first as a researcher, and then you go, oh, okay, I can explain away the 18 and the 31, but not the 10 or the 6, because the 18 and the 31 were covered by a rain warning, for example. So you need to do more work, but it's an example of how you can very quickly use some of these statistics, probability of detection, false alarm rate, etc., to communicate with scientific colleagues or other people who understand those terminologies about the important aspects of your system. But you first need to do the understanding work yourself so that you make sure that you're communicating something that's very relevant. So it's your job to decide what's relevant, and then you can use these statistics to communicate and compare and contrast with other forecast systems. So something you could do is go to the Bureau's external web page, look at their skill in forecasting in general, and then if you come up with a forecasting system for server load, you can tell your manager whether it's more or less accurate than the weather forecast. And I like that idea. All right, so that's the Slidey Bit. Now we've got a tool that I've I call it a sketch of a piece of software. It's not a real piece of software. It's something I built for myself to demonstrate concepts and potentially deploy. And then, with luck, a little bit, there'll also still be time for a bit of conversation about future, where I see some, maybe a bit pie in the sky, but ideas about where open source could help take this kind of software and analysis further. So, is it running? Yes, it's running. Okay. Is it reasonably viewable on this projector? It is now reasonably viewable on this projector. Okay, so this is my first web application ever. You can tell because I used Bootstrap, which is a wonderful, wonderful tool. Everybody should just use Bootstrap. Okay, so this is, for me, it's a mixture of, it's an all-in-one data collection, analysis, experiment, and learning environment that could be used on a server in a kind of, cloudy, everybody can look at it kind of way, or an organizational, there's a project and everybody can use it kind of way, or I've got a bunch of stuff on my laptop I'm hacking on kind of way, which is pretty much mostly how I use it. So it consists of currently running experiments. So experiments, just think of it as like your project directory. A learning environment, which I'm quite happy about. So the concept here is that if I need another developer to be working on verification, I don't want them to be struggling to know how to do it, and I don't want them to be short of resources. So most of these videos are internal. I'm hoping after PyCon I can add one to this that's, that everyone can watch. But we have something like 22 hours worth of video on this specific topic that we've accumulated internally at the Weather Bureau. So straight away, if people want to go to the underlying, the original developers of a lot of these skill scores are still around, and they're still working, and they're pushing the envelope in terms of, spatial analysis and probability analysis, and all of their work is available to any developer. As well as that, worked examples of how to come up with these scores are available through the IPython notebook. So straight away, if you need to take some techniques, you can view how they're applied in an isolated and specific way that concentrates on that particular score or technique, and then you can take that away to your piece of software. So straight away, you've got this sort of this worked examples, laboratory kind of experimental environment. And those notebooks, they're all live, and they all have access to all of the data and all of the experiments so that you can just hack on them with reference to all of the data sets that you've got to your heart's content. Notebooks are amazing, but they're not a very good way to build software, as a system. They're not a system software tool. They're an amazing experimental tool, fantastic for exploring something, sending to someone else and sharing, but they're abjectly horrible at trying to actually build an entire system out of. You would never try to, I would hope you would never try to run them through the IPython notebook command line extension in cron, for example, to support your system. You really should be going and building things. And that's what these experiments potentially are, is that these experiments support the sharing of code. So in this, we've got some code here that's processing one of our data formats, converting them into areas, etc., so that if you question a result that someone has shared through the data tool, you go straight to their code. There's no concept of asking them to release it as open source, and even if they're not, version control, even if they're not on, using Git or whatever your company uses for version control, even if they've just got something on their desktop that they've been hacking on, in their lunch hour, they can still give you a URL to their desktop, and you can just look at their local installation, and you can just inspect their code. So one of the things we do have trouble with is, legacy code that was developed outside of the normal project hosting repositories, things that just exist on people's desks. If people were a bit more willing to expose their data in their code as an ordinary practice, and get a little bit less worried about whether it's perfect or ready for operations, or whether it's been through code review, and just go, hey everybody, this is what I'm doing. If you really want to know, that's fine. I don't expect you to read it, but it's available. So first of all, the code's available. The data is very inspectable. So in this case, we've got largely, this is the contents of an AXF file, and it's basically a combination of CSV sections and, key value pair sections. So you can go in, you can inspect the raw data, you can move it through a pipeline process and start inspecting it as structured data. So if you're putting together some kind of processing pipeline, first of all, that's good practice. Not everyone's going to have a methodology about how they approach an experiment. This provides just one potential methodology just out of the box. It's inspectable. You haven't had to do anything. You haven't had to load your data into Microsoft Excel. You haven't had to write a conversion layer. We'll see in a couple of minutes, if I've still got time, although I'm fast running out. I'm good? About how more sophisticated data types can be inspectable through this web interface method, and how automated plotting and automated charting can support data discovery and data investigation in new ways. So that's something that's often, for me, has been an assumption of a lot of scientific literature, is that you already somehow understand a fair bit about the data that you're working with. Whereas if you really don't, if you're just given some file and say, well, this just has like arrays of data in it, and you need to work out how the vectors are represented, are they speed and direction, or magnitude, are they magnitude and direction, or U and V, and what does it look like? There should be this period of play where you're learning your data beforehand, and so that's an explicit step. Analysis results. So this is lead time in minutes by distance error in kilometers of thunderstorms. So if you look at a thunderstorm warning in half an hour's time for this particular data set, there was a 22-kilometer error on the center, effectively the center of mass of the thing. So this particular data set, these thunderstorms went off track quite fast. This is basically, I got this for free out of Pandas. It just supports plot my data and something comes out. If it's simple data, something meaningful comes out. If it's complicated data, something meaningless comes out. So supporting some configuration on that is down the wire. But the point is that even though it makes no sense not to plot the lead time as the x-axis, I can actually still follow through the samples and go, what lead time did a particular distance error occur? So no, this is not a professional plot. Yes, I can just look at it and understand what's going on. So I think I would never include this in a publication. I would never ordinarily include this in a presentation where I cared about where communicating the results was important. But when you're not at that level, when you're at the what's in my data and what's going on level, it's just perfectly fine just to be able to click and look and click and look and click and look and support the first hour and a half of looking at what it is that you're working with. And then there's other aspects to this. So shareable images, everything gets a unique URL, shareable code, and support for writing up your reports in Markdown with links back into the rest of the system, so that when you're writing your reports, the inclusion of graphs and things like that is quite straightforward. And as well as that, if someone's reading your report or reading one of your graphs on the system, they know that they can get back at the data that created that graph. So if they have a question about, what did he do? Why on earth did you not just use the x-axis for lead time? What's going on there? They can just go back and just download that data and play with it. And if I've missed the hidden variable and they want to go, I wonder how this relates to which month it is. Does it vary by month? It's pretty easy for them to just get at and share the data. So look, I don't know whether this is an amazing idea or not. It's just something I wanted to talk about. So I would like to encourage everybody to not feel too critical of it and feel like it's an okay thing to just share random software. It's a software conference. I think we should be allowed to just talk about the ideas that we've had. So I'm going to shoot back to the final 2 or 3 slides of this presentation now. And then I think there should be some room for discussion. So one of the main things is the skills you need to do this are come from a lot of different disciplines. And if you're coming at this for the first time, it can be very confusing. So mainly you're going to want to work in a team. If it's a professional context, you're not going to want to do this on your own. Probably even if you want to do it for personal interest, you should do something like jump on Kaggle and find some random people on the internet and, hey, crazy, let's get to know each other and write some code. But you should expect that it's going to push you in ways, push you to develop knowledge that you don't have. Now, I added the zone of confusion. I feel like it's important to acknowledge zones of confusion in life. I think it makes me feel better anyway. But whoever put this together is just bang on with the original image. Okay, so tools for the future. So enhanced data browsing, I've talked about. I think that that's really important. The ability to just throw files at a system and have almost any kind of visualization of what the data is underneath, and have a system that's competent at assessing and showing data. Intelligent databases that the reason I say that is because actually data is hard to move than code, and it's hard. So if you have a database that naturally supports, like if everybody had a data tool and the data tool actually worked and it was actually really good, then anyone who had the data could do some kind of pretty easy inspection, pretty easy results, pretty easy R-squared, RMS, really good support for these. And your tools would just kind of come with the data. So that's what I mean by intelligent databases. So at some level, it's important to split the database off because it's a separate concept from the system. But at another level, when you want to share and collaborate, the tools are becoming so complex that you kind of need to you need to share your environment these days as well. And I mean, that's why the cloud is such a big thing. It's because people don't want to be their own system administrator and cope with the version changes of these scientific libraries and run through and make sure that everything still works. They want that to a degree to be done for them. And that's I guess, where I think open source could come in, is by providing, as it already is with like the IPython notebook, people have just revolutionized how like enormous numbers of people look at problems. But it can go further. There are other aspects of data analysis that that IPython notebook isn't really about. So data sharing is huge. If you're trying to, and it's very real. Like I tried to enter a Kaggle competition. The data download was something like 300 gigabytes. Chrome didn't support data download resumption, and I needed a cookie to download the data. And the server was in the US, so I didn't get a fast download speed, and no one made it available via BitTorrent. And so it took me 2 weeks of 20 minutes in the evening units of time to actually complete the task of downloading an entire data file, by which time I got sick and then didn't do anything for a fortnight, and then it was 2 days before PyCon and just nothing happened. So, these barriers to entry really stop people. And, everyone thinks we live in this amazing time of broadband and cloud and computers are free and disks are cheap. But they're not actually cheap enough that I go, you know what, I'm going to spend $20 on an Amazon EC2 instance to do a regression analysis because I just feel like it. I think I might go, you know what, I'd actually really rather just run something on my laptop for free on a smaller data set. So actually, I think in terms of supporting play and open communities and learning, I actually don't think the tools that we have are there. So for example, if the data tool magically somehow sat on top of a BitTorrent layer that wasn't full of random content, you could actually have sharding of data across a bunch of people who are running data tools. You could have an open, genuinely open source, distributed way of sharing the data to make the downloads more accessible if it was open data. Of executing on other people's, small components of these things, if you can distribute in a supported way, and really allowing a much more open scientific community. And I think we could move that way by making those tools better than the ones that you get by paying for them. And I think that that's an interesting concept.